All right, good morning, everyone. Thank you for coming. I appreciate everyone being here as we come into day 3 of the Geo-Extreme 2025 conference. We started this conference on a Saturday with an exceptional field trip to the Palos Verdes landslide. And when Daniel and I were thinking about the hazards for this conference, we've talked about seismic, we've done wildfires, but we couldn't leave Southern California without talking about landslides. And not just any landslides, we're talking about Texas-sized landslides, so we're talking about mega landslides. So that's what our last plenary session will be on today. Before we start that, we're gonna have a presentation from the younger members. I'm gonna call up Dr. Eric Jensen to lead that. Thank you.
Good morning, everyone. My name is Eric Jensen. I work at the University of Colorado Boulder, and I'm also the chair of the Outreach and Engagement Council for the Geo-Institute. Under the Outreach and Engagement Council exists a new-ish younger member committee where we're trying to reach out to the younger members of the GI and get them engaged, particularly at the national level. And one of those efforts involved a competition where we invited young practitioners, young in this case is under, or I think 35 and under, to give presentations, short presentations at a technical session here at Geo-Extreme, and then we did it at the last Geo-Frontiers, we'll be doing it at Geo-Congress again here in Salt Lake City. And who we were going to see today is the winner of that competition from our session on Monday. So I'd like to introduce from Langen Engineering, Eleni Kyriakou.
Good morning, everyone. I'm Eleni Kyriakou. I work at Langen out of the New York City office, so a little trip out west for me. And I'll be talking to you all about our efforts at Langen of building a neighborhood for the future at Willets Point in Queens, New York. So quick presentation overview. I'll be talking to you about the history of Willets, what we envision for its future, engineering challenges, and the good stuff, the solutions to all those challenges. So Willets Point, it seems like most people are from the West, and I don't know how familiar you are with New York and New York City. You might just know it as the Big Apple and that's it. But New York State is pretty large. That right here, this red bubble is where New York City is. If I zoom in, this is where Queens is. This is all the boroughs as well as Long Island, but we're gonna zoom into the Flushing neighborhood of Queens, New York. So Willets Point is the area in green. It's 61 acres of land. To our north, we have LaGuardia Airport. To our south, we have Arthur Ashe and the Louis Armstrong Stadiums for tennis fans. That's where the US Open is held. To the west, we have Citi Field, home to the New York Mets. Congrats to all the Dodgers fans for your win, but go Yankees. We also have some sensitive transportation infrastructure near us. We have a DOT elevated highway to our north, a New York City Transit elevated line to our south, as well as a DOT bridge to our south. So the history of Willets is very important. In the 1900s, the New York City area was using coal to heat their homes and for industrial purposes, and they were taking that ash and just dumping it at Willets. And then in the 1930s, the area became a little bit more urbanized, and they decided not to put residential housing because of, the coal ash. Let's just put some auto body shops, some filling stations, and we'll call it at that. So it was like that until very recently. You would just walk by and see all these auto body shops. In the late 2000s, early teens, there was an initiative by the governor and mayor to give Willets a facelift. And so that's when we came on board. So we came on board in the 2010s, but it wasn't until a decade later, until we got boots on the ground. I did the initial geotech investigation in 2019. And that's because this is 61 acres of pretty contaminated land, and I'll talk to you about the other challenges as well. And so we had to get developers and contractors and the community boards and government officials and a whole bunch of people on board for us to even get to the site. So in the 2020s, we did remedial work and we started construction, and we're hoping for the next decade to show a new Willets in phases 1 and 2 and a start to phase 3. So what are those phases? So here's a quick overview. In the center, we're gonna have the first soccer stadium in New York City. So this is gonna be a really big sports hub. For the New York City Football Club, we're gonna have a school, affordable housing, residential, shops, parks, you name it. It's just a completely new neighborhood in Flushing, Queens. So the challenges. This is 61 acres of land, right? It's 61 acres of land that's within a flood zone. So if you go to the FEMA maps, you go and you find your site, and our site is telling us that we have to go to elevation 12 to 13 for flood resiliency. That is already above what existing grades are. So we have to now look at the New York City Building Code, which has a requirement that you have to have additional 2 feet of freeboard. So that's 2 more feet of fill that you have to raise your site in order to have some flood resiliency. So that's 61 acres of land that has to go up. Next, obviously, all the contamination. There was not too much oversight in the 30s about what you could do. So these auto body shops were just dumping oil and gas and tanks and car parts and bowling balls and you name it below the ground. So we had to remediate all that soil. And also the infrastructure wasn't for residential. It's not gonna meet the demand that we want for our future vision of Willits. And whatever is there is outdated, it's very inadequate, and it's decaying. And finally, the good part, the geotech aspect. So we have 300 data points in this area, and we can see some variation from the north to the south of the site. The southern half of the site is really where the bulk of our work is at the moment, and it's where the biggest concern is because there's 60 to 80 feet of underconsolidated, super soft, soup-like clay, as well as silt and peat. So who would want to develop on this kind of ground? If you walk around the site, well, things have been better now, but if you did a few years ago, you could see a pile-supported footing and all the ground around it settling. If we did a test pit, this is a picture of mine from 2019, the settlement of the roads and sidewalks were handled by just going in and putting more asphalt, and that's more weight, so that's more settlement, and then they would come back and more weight and more settlement, and it would just never-ending loop. And then the site itself was it was a flood zone without flood. During a normal rainstorm event, there was just puddles and inches of rain on the site because the clay was not allowing it to drain. There was no infrastructure, no stormwater management, and it was just a mess at the site. So the solutions. First and foremost, we have to make sure that the site is flood resilient for the future. So we have to bring the grades up a minimum 2 to 9 feet, and that's on top of all this clay that I was mentioning. We also have to worry about all the edge conditions because we're making this new neighborhood, right? But we still have a whole other part of Flushing around us. So while we're putting our own streets, our own infrastructure, our own buildings, our own neighborhood, we have to make sure that everyone can access it. So even though we're putting roads, we have to make sure our roads attach to the roads that exist. In some cases, that means we have to add 10 to 16 feet of fill just to be able to access the site. So while contamination and infrastructure seem like environmental and civil issues, it becomes a geotechnical problem when you actually have to go in and do the work. We installed and designed supportive excavation systems for all this work. That could go up to depths of 20 feet below grade, and that's in high groundwater and very soft soils. So you see the challenge in that. So when we actually went in and did this, we were able to remediate and replace 169,200 tons of contaminated soil, and our civil team was able to help with the installation of 5,400 linear feet of utilities. And this is only to date. This is for phases 1 and 2. Phase 3 has not begun, so this number is only going to grow. And here is what I've spent a lot of my career on, the foundation design at Willits. So we have a kind of checklist of everything that we wanted to hit while we were picking our solution for a foundation system. we really, really wanted to do soil improvement. We wanted to be innovative, and it just didn't work for our schedule. It didn't work with the agencies. The cost was not where we wanted it to be. We went granular. We did a few iterations. It wasn't where we wanted it to be. So we had to look at piles because obviously you're not putting shallow foundations on this soil. Piles to rock would have been ideal, but rock is over 300 feet down, so you don't want 61 acres on stilts. Next, we looked at driven piles. The cost of steel has gone up in recent years, so that was not so great. In terms of schedule, driven piles are typically faster to install, but we have to go really deep to hit bearing material, so that means you have to splice the piles, and that adds time, so it's not helping our schedule. And for agencies, I don't know about how it is out west, but in New York City, they're pretty strict about what they have for vibration limits. So we couldn't drive any piles near the DOT to the north and the south and New York City Transit. It was a mess, so we just wanted to avoid that. And then we were like, okay, drilled piles, let's do it. Concrete's a little bit cheaper, we'll make it work. So we looked at CFA because it's a really good option, but it's gonna create spoils, and we don't wanna do any more remedial work than we have to. Hopefully those spoils weren't contaminated, but was still gonna, you still had to do in situ testing, and it was gonna add time to the schedule. So what did we do? We went with a drilled displacement pile. So it met everything on our checklist. The constructability was okay, the cost was where we needed it to be. In terms of schedule, it met that requirement. Agencies were fine with it. There were no spoils. We were able to be a little bit cost and time efficient because we would be standing next to the rig while they were installing it. We would see where that clay layer ends with the driller, and we would decide right there and then, okay, we only need to go this amount of feet to have the bond length that we need, so we could save some time and cost. And then for settlement, we did our analysis to make sure that the differential settlement was okay and that was within any of the project constraints we had. And then finally, we had to look at drag load. So all of this clay that's at the site is self-settling, if you saw that first picture. Even if we install our piles, all that clay is gonna just keep going down as the years go on. So it's gonna be dragging down the pile. We needed to do some testing to make sure that we were getting the right amount of bond length and strength to all of our other materials so that this drag load wouldn't be detrimental in the future. And we did so by doing load tests. We did our standard ASTM and New York City Building Code 200% of design load test, and then we did excess loading. And most of the piles were tested to the capacity of the test frame. I don't remember any actually failing, but we were able to see just how much of the load was dissipated in the clay because we had strain gauges within the layer and within the bearing layer, and we were able to determine what lengths and bond lengths we needed. So to date, we have installed 3,700 piles within phases 1 and 2, and this kind of encompasses everything I mentioned. So for the buildings, pretty easy, pile caps, piles. Everything else that has to be raised up to flood elevation was pile supported. So we went in, remediated, put our piles, put a platform, and then on top of this platform, we put clean fill. Within the clean fill is the utilities. I'll kind of highlight. So this is like some utilities that we had to install. Then we went up to design flood elevation, and then we put roadways, landscape, hardscape, made it beautiful, right? So this is what we envision it to be by the 2030s. I've been on this project since 2019, since the second week I started at Langen, and it was a challenge. It still is a challenge, but it's really exciting, and I can't wait to see just what the future holds at Willits. Thanks.
Good morning, everybody. I'm Tim Stark from the University of Illinois. So we have 3 mega landslides for you today, 2 of them from California and 1 just over the border in Portland. So we're going to start with Portland. Let's see. Oh, there we go. Okay, and Andy Kost with a senior principal, associate geotechnical engineer with Conforth Consultants in Portland is going to give the presentation. Andy has about 13 years of experience in geotechnical engineering on a wide range of projects, including landslides. Andy's presentation today is titled Washington Park Landslide, Reservoir History and Modernization. So, Andy? Okay, there you go.
Thanks, Tim. Good morning. And I think you might find a common thread for our presentations today to be that some landslides you stabilize and some landslides you name. And this is certainly one of the latter category, and I think we'll see a few more of those. So I'm going to talk today about the Washington Park landslide, and this is a prehistoric landslide, but in more modern times it's had some significant impacts on the infrastructure for the drinking water supply of the city of Portland, Oregon. And so while there's a lot of different aspects that we could talk about with this project that would encompass a pretty wide range of technical interests, what we're going to talk about today in this presentation is focusing on the monitoring effort that both allowed us to develop a pretty efficient design for this project and also helped us to manage the risks during construction. So the city of Portland sources its drinking water supply from the Bull Run watershed on the northwest slopes of Mount Hood. And that water is captured in a couple of reservoirs up along the Bull Run River and then piped down about 30 miles to the city. And this system was conceived in the late 1800s. There was some storage on the east side of the Portland, and then the water goes under the Willamette River and comes up to its terminal storage at Washington Park in the West Hills of Portland. And that area was pretty much the furthest that they could gravity feed water from this watershed. And it also provided them a nice elevation for servicing the downtown area, so that was the reason it was selected. So the first conduit was constructed 1893, 1894, carried about 25 million gallons a day of water down from the watershed to the city. And they needed to find a place and create a place to store this. And so on the west side, they located some sites in the Tanner Creek Basin, and they constructed a couple of concrete gravity dams there. Those were referred to as dams 3 and 4, which held reservoirs 3 and 4. So you can see in this photo they're working on the mass concrete structure for Dam 3. And they finished those concrete gravity dams up, and then they laid back the slopes of the valleys in order to increase their storage, surfaced those with concrete, and prepared to fill those with water. Now here we have a photo of Reservoir 3 prior to first filling. We're looking here from the north towards Dam 3. And you can see on the right of that photo there's a feature that wasn't in the original design drawings. And so as we dug back into the documentation for the project a bit, we found that they had recorded some significant cracking in the concrete liner shortly after it was first constructed there. And they had encountered some fairly rocky material when they had excavated through that portion of the hillside, and also quite a bit of water that was borne on that rocky debris there. And so they interpreted this to be a local stability issue. They put back this concrete buttress and also dug a little drainage tunnel through the hillside back there, patched everything back up, and then were ready to fill the reservoirs. And so this is a photograph of what that would have looked like around the time of first filling. We're looking from the south now, so Reservoir 3 is the upper reservoir in the distant part of the photo. Reservoir 4 is down near the bottom of the photo there. So they brought those reservoirs online, but it wasn't too long before they started to see some more issues at Reservoir 3. So this is a photograph of that same buttress area that we were looking at previously. Now we're looking from the opposite side of the reservoir. And they've dewatered this reservoir again because they started to have some significant cracking show up on that west slope there. And you can see that it encompasses that buttress area plus a little bit more area. And if you squint towards the upper part of the photograph, I kind of feel like I might be able to see a little bit of offset, vertical offset in that road up there. And it wasn't long after this that we started to see some issues pop up at Reservoir 4 down the slope. So in this photograph, the most dramatic part of the photo is sort of that shallow slough that deposited a little bit of debris over the railing of the reservoir. But really the concern is all of this cracking that is starting to show up on the uphill slope of that reservoir as well. Now the city engineers, they realized that they had a slope stability issue, but they were a bit puzzled because they were anticipating more of a circular type of failure surface. And so they were scouring the hillside kind of in the roadway up above, looking for ground cracks to show where the headscarp was. And they couldn't find any. And so they were puzzled for a couple of weeks until they got a communication from the cable car company that had tracks about 800 feet up the hill saying, hey, our tracks are coming out of alignment. Do you know anything about this? And then they realized they had a much larger issue on their hands at that point. And so that kicked off a round of much more detailed investigations and characterizations of the slide. And we're fortunate because the city engineer recorded a lot of detail from these investigations in a paper that was actually presented to the American Society of Civil Engineers back in 1904. And this was like a 50-page paper, so we have a tremendous amount of detail on what they were finding in that. So I'm going to walk you through a little of their initial investigations there and borrow a few images from their paper here. So here's a map of the slide that they defined. Reservoir 3 and 4 I've outlined there. And the first thing they did was to get some ground survey on a grid pattern there and try to figure out where things were moving and how fast. And then when they had a general idea of that, they went through and they started putting in a bunch of churn drill borings. So each of those orange dots is a churn drill boring that they went through and got a very rough characterization of the slide debris that was moving. The more important thing they did with these borings is after they completed a boring, they would sleeve it with some steel casing. And then they'd come back once a month, they'd run a probe down it and back up, and they were figuring out where it was pinching off. So we didn't have any measurements of movement downhole, but they were at least able to determine the depth of the slide movement. And what they found is that the slide was about 1,700 feet long, about 1,100 feet wide at the base, 250 to 300 feet in elevation difference from the toe to the head, and it was anywhere from 60 to 130 feet deep. They knew they didn't have enough information still to really understand how the slide was moving or what they could do about it. And so they came back, and each of those yellow diamonds represents a 3-foot by 3-foot diameter vertical timber crib shaft that they hand excavated down through the slide debris to the top of rock. So this was a really time-consuming exercise for them to go through and characterize this, but they really didn't have any of the other more modern instrumentation or drilling techniques that we have, and so that was what they came up with. And from that information, all those shafts shown in yellow, they were able to get a pretty good cross-section of the slide as it passed through the reservoirs there, and able to define that boundary of the slide plane. And what they found is when they got down just above bedrock, they had a picture here of some clay material that they found, which we now know to be an inner bed that was between different basalt flows at the time. And they could see that it was very polished and slick-and-sided, and so they correctly identified that this was their slide material. They didn't have a way to measure residual strength. They didn't understand effective stress, but they knew that this was a part of their problem. They were also able to get an estimate on volume. So just for interest, they estimated that landslide to be about 3.5 million cubic yards of material. And all of this accelerating movement that was caused came from excavating about 60,000 cubic yards, or about 2% of that mass at the toe. So I think the people in this room understand that when you're close to a factor safety of 1, it doesn't take a lot of change in your weight distribution, especially at the head or toe, in order to cause some big changes in rate movement. The other thing that they encountered as they did these shafts is they encountered some very shallow groundwater in the slide. And this was a problem for them because they're hand excavating, and so they can't advance the shaft while it's filled with water. And so they would pump these shafts, and some of them they would pump for a couple of weeks, some of them they had to pump for a few months in order to dewater them enough to construct the rest of the shaft. And what they noticed from their ground survey is that the slide was slowing down while they were pumping. And then when they would finish a shaft, stop pumping, that slide would pick back up in rate. And so they understood that that water was really a key contributor to the slide movement there. And so what tools do they have at their disposal back then? Not very many. They can't remove that clay. They don't have a lot of structural options to stabilize this, but they could deal with the water. And so they came up with this concept of constructing tunnels to reduce that rate of movement, which was about 15 inches per year at that point, and put these tunnels along the shear plane and gravity drain that water from the top of the slide out through the toe. And so between 1900 and 1906, they put in over a mile of these tunnels, and they were actually very successful at reducing the rates of movement, with that rate being about a little over 1/8 of an inch a year at the time we were getting towards construction of this project. So to put a little bit more detail on those rates, we don't really know how fast that slide was moving at the time they initially reaccelerated it. But at the time they started to investigate over the next couple of years, it was moving about that 15 inches a year. They started dewatering for these shafts. It knocked it down actually by 90%. So that was a big eye-opener to them. They stop dewatering, that rate starts to rebound, and then they start putting in these tunnels over a couple of phases, and that brought the rate down to about a 1/2 inch per year. And then over time, that rate has gradually decreased as that drainage has been a little bit more effective, and we start to have a little bit of change in the weight balance between the head and toe of the slide as it keeps moving. So really, this was remarkable mitigation for them at the time, to be able to change the rates like that. 1/8 of an inch a year still adds up over time, and so the Water Bureau, over the following decades, still had a lot of damage to their concrete and other facilities that they had to continue to address. They eventually lined the reservoirs with a Hypalon liner to try to reduce the frequency they had to touch up the concrete. But eventually they were getting to a point where they knew they had aging infrastructure they had to address. And as they kept going, they also realized they had more seismic resiliency issues that they needed to address. And eventually we're going to have to respond to some federal requirements to cover their drinking water supply. So that's where this project began in order to improve the existing reservoirs there at the Washington Park area. So the concept that was selected is to replace the existing Reservoir 3 in the upper portion of that image with a new buried reservoir, convert Reservoir 4 to on-site storage drainage measurements, on-site surface water management in order to handle any runoff or off-gassing they need to do, as well as to be able to buttress the slide a little bit in that area. And then both of those areas would get a reflecting pool because they're on the National Historic Registry, so we had to maintain that historic character of the site. And all of this had to happen within the footprint of this active landslide. So how do we do this without repeating the same mistake that they did originally by cutting indiscriminately into the toe of a slide? Well, we had some things working in our favor this time as we approached the landslide design, and one is we have a tremendous amount of monitoring data. So we have the survey data that goes back to the 1800s that tells us how that slide was behaving over time and the effectiveness of that drainage. But we also have slope and clinometer data. It goes back to the 80s, and not just at the site, but all the way up the hill as well throughout that landslide. And so you can see from this plot I'm showing you here for one of the SIs that behavior has been remarkably consistent over time. You'll see some years are a little wetter than others. It might have a little bit more movement. It tends to move a little more in winter than summer. So very precipitation influenced. But overall, very consistent rates. And so we interpret from that that drainage has really been very effective at managing groundwater fluctuations within the slide, and that is helping us to limit those slide movements. So that allows us to accommodate this movement rather than trying to stabilize the slide. And in order to do that, we can isolate the new reservoir from the landslide. So the way that we did that for this project was by designing a compressible inclusion to place between the landslide and the reservoir. So as this compressible inclusion consists of a zone of engineered expanded polystyrene, or EPS, that gets placed between the slide and the tank. And as that slide moves, it's going to crush that EPS and impart a much smaller and more predictable load on the tank. And then we also have an MSE fill that goes in between the slide and the reservoir for a couple of reasons. One is we needed a place to build some of those visual features, but it also helps put some weight on the toe to counteract the removal of water. Now that we no longer have an open reservoir there, we've actually taken some weight off of the toe of the slide by removing that water. And then there's a little concrete toe block you'll notice there. The purpose of that is to get us up a little bit to start that MSE wall, so we don't have to cut back so much into the toe in order to get our base width for the MSE wall. So this is a picture of what that looks like. Engineered EPS is going in just as blocks that are trimmed to be flush with the MSE wall on your left and the tank on your right. And all of this, of course, fits within a much larger project that included shoring that allowed us to offset the reservoir from the existing toe of the slide a bit. We have a lot of drilled shaft foundations that were supporting that new tank, visual feature elements and park elements on top. But really the key part of that landslide design was the compressible inclusion. So let's talk a little bit about how the landslide responded during construction. This was a project that lent itself very well to the observational method, and what we used some specific techniques to try to manage those risks of having to make some excavation to the toe during construction. So we'll look today just at a small section here of the MSE wall construction. So that's the green area I've shaded there, and we're going to look at a particular inclinometer, SI8 here, and this is an inclinometer that was installed with an IPI string, and so we were getting very frequent readings of how the landslide was responding to the changes we were making at the toe. So I'm going to show you a series of photographs here on the left that illustrate the progression of construction, and then on the right we'll look at how the slide is responding to that using that inclinometer. So we have kind of a base rate of movement going in, and the reservoir is dewatered at this time, and so that rate's actually just a little bit higher than the pre-existing rate because we've taken a little bit of weight off the toe there. And the first thing the contractor was allowed to do was to get in, and they could strip the concrete liner and excavate for that toe block over just 50 feet of the reservoir. So we're using these closely sequenced excavation methods with a required backfill before they can progress to a new segment in order to manage how much weight we're taking off the toe of the slide at any given time. So this wasn't very much. This was 6 inches of concrete liner, 100 cubic yards of material at the toe for a 3.5 million cubic yard landslide. But do you think it felt that? It did. At least the lower block of the slide did. Because we're changing the stress conditions at the toe. And so you saw an immediate response where that lower block accelerated, and then the contractor had to put back concrete in that hole within 24 hours, and you see it immediately starting to slow back down at that time. And so we progressed with that sequence in 50-foot segments, moving from south to north there, and you can see with each of those segments we saw a similar response, where we'd have that initial acceleration, and we'd have a deceleration as they backfilled. So what this was telling us is that the slide is responding in a manner that's consistent with our geologic model of the slide and how we would anticipate it to respond. So after we got that toe block complete, now we need to make a bit of a cut into the hill to get that MSE wall keyed in. So there's a little bit more of an excavation. We're probably looking at more like 400 to 500 cubic yards here. We put some of that material actually on the slope to the north of it, so it's actually not off the toe all the way, it's just in a different place. But as you can expect, more weight changing, more response. And so, again, we're zoomed in on this. We have a pretty tight scale on this vertical axis here, so we're looking at just a 1/4 inch of movement or so. But it definitely is responding to that. And then over time, we kept building the MSE wall back as we were expanding that excavation footprint, and we were kind of chasing ourselves for a little bit because you had to get a fair length of your wall exposed in order to be able to build up some height. And so that movement continued to progress for a couple of months as we caught up with the weight there. So I'll zoom out this plot of slide movement rates now, and the green arrow shows where we're at in that sequence, and we'll just walk through the rest of the MSE wall construction. So you can see we're starting to get about halfway up over a limited length there. Now we've got that about halfway up over most of the landslide toe in this area here, and we can see that the rate's just starting to slow a bit. And finally, we get that MSE up to design height over about 2/3 of its length, and we finally caught up with the amount of weight we had removed, and that slide is starting to stabilize. So while I'm not going to get into a lot of the detail on how we were using this information for construction decisions today, we did have a framework in which we were monitoring each of these events as it went and assessing them within a risk framework and different tolerable thresholds that we had in order to make decisions on how construction could progress. But I also wanted to show how the effect of this up the hill from the slide. So we had instruments not just down there at the toe, but throughout the landslide. So you can see this is the same data we were looking at from SI8 down near the slide. There's the start of the cut with the red line, and this green arrow shows substantial completion of that MSE wall. And we're obviously above our historical rate there. If you look at the next instrument up the hill, you can see that we had a response that's very similar in sort of the overall trends, where an initial acceleration followed by deceleration. But there was a delay in when that occurred, and the changes were more gradual. And that continued to hold as you moved further up the hill, where we had an increasing delay in movements. And in general, the changes were more subtle as you went up the hill. And so this is consistent with a lot of behavior that we would see for an extensional translational landslide, where the slide is extending from the toe as that support is removed. So at the start of construction, we would have had varying degrees of internal tension cracks that would have existed within that slide. And you end up seeing these different blocks that tend to move within the slide. So you make that cut at the toe, that lower block is going to respond right away. And then in the process of doing that, it's going to reduce the stability on the block that's uphill from there. And you have what you might call this train car effect or something, where it moves in these blocks progressing up the hill. And because we're doing this in a way that's removing support unevenly at the bottom, we have different levels of stress redistribution that are happening. It tends to sort of diffuse that, the suddenness of that response as you move up the hill. I also wanted to show you a bit about what it's been doing since construction. So we talked about how prior to construction we were looking at a little over 1/8 of an inch a year of movement. During construction we peaked out at about 0.86 inches per year. And that was a total of just under 2 inches of movement over about 4.5 years. So, we saw about 14 years worth of movement in 4.5 years. We consider that to be certainly an acceleration, but a manageable change in rate. And since that time, we've been averaging just under 1/10 of an inch a year. Now, I don't know if it's going to remain below that pre-construction average indefinitely. We've increased the factor of safety only very slightly over the pre-existing conditions. And that really wasn't the intent of design to reduce the rates. It was really to accommodate the rates. And so what's encouraging to us is that we're seeing rates remaining within that range that we anticipated during design. So I just wanted the thoughts I wanted to leave you with today. We were very fortunate to have the level of monitoring data that we did for this site. And we were really able to leverage that in order to design for this slide in a way that we were able to accommodate movements and able to manage construction risks associated with this approach rather than trying to have to stabilize it. And so, again, data is always our friend, right, as engineers, and the more we can leverage that, the better. And so far, the post-construction data is indicating that landslide movements are within the design range. So I'd be remiss if I didn't leave you with a before and after photo at the end. This is, again, Reservoir 3 looking towards Dam 3. And this picture was taken about 10 years ago prior to the start of this project. And Today, that reservoir has been brought online. It's providing water to the city of Portland. The visual features are there. We have a park space on top. And like most things I've built in my life as a geotech, all the stuff I did is underground and never to be seen. I took my kids through there for the grand opening, and they're all like, okay, what did you do? But we're happy that we have the seismically resilient water supply now, and all indications are is that the landslide mitigation system will be able to maintain this for a long time to come. So thank you. I understand that we're going to save questions for the end, so I'll stick around after this if anyone wants to talk with me. Thanks.
Yep, we're going to save the questions to the end, so please don't forget questions for Andy at the end. Okay, our next presentation. Nope. There we go. Let's see. Okay. Our next presentation is by Dr. Neven Matasovic. Neven is a senior principal and lead for the geotechnical practice at Geo-Logic Associates here in the LA Basin. Neven has over 35 years of experience in geotechnical engineering and has worked on a wide range of projects and has made also significant contributions to seismic site response analyses. Neven's program DMOD was one of the first nonlinear site response programs. So in addition to that work, Neven's been actively involved in the Portuguese Bend landslide complex. How many people attended the field trip on Saturday? Good, a few. So we had 2 bus loads, about 75 people or so going out to Portuguese Bend. Daniel Pradell was the key driver of that field trip, and it was really great. We saw a lot of interesting things. Hopefully Neven's going to talk about some of those, like the tow uplift that we saw along the beach, which was just stunning. So today, the title of Neven's presentation today is Mitigation of Portuguese Bend Landslide Complex. Neven?
Thank you, Tim. So now we will switch from inches to feet, from feet to square miles, and I'll show you why and how. So I will start with what I call Portuguese Bend landslide trivia, just the key, information. I have to touch geology. I have to talk a little bit about geology, cause, and impacts on landsliding. Then I will share you a little bit about bumpy path to mitigation, and you will see what that means. Then I will focus on the remedial design and implementation. There are a few conclusions and takeaways to make, and a few acknowledgements also to make. So where is the Portuguese Bend landslide or landslides? And how big are they? So here are the landmarks in Southern California, so Dodger Stadium and Disneyland. So those of you who visited Disneyland is, and I'm talking Disneyland and California Adventure and that nice parking structure they have, it's a square mile. Well, my favorite landslide used to be a square mile before it started moving, and it's now 3 square miles. You see the orange arrow in the bottom of this slide. This is approximately where a beach close to my house is, so I'll show you the view how it looks like. So this is how it looks like. I go to the beach 3 times a week. I never can stop thinking about this landslide because this is how it looks like, and let me annotate it a little bit. So this Portuguese Bend, this is the original, this is the best known. This is about, 1 mile, and this, what we now call Altamira complex, which started moving in December 2023, 3 square miles. What I also have shown here is indicated is VVG, which is Valley View Graben. This is what our geologists think water is coming in. Water is coming in from a higher elevation and then ends up at the toe. Notice also how this is, relatively flat. This is not, kind of, steep slopes. They are relatively flat slopes, but they move, and they do move pretty well. So, few highlights about this landslide. It used to be the largest landslide in the US. It allegedly started moving in 1956. Portuguese band landslide failure plan was, at least everybody or most people thought, was 150 feet deep, moved about 12 feet a year or half an inch a day. So relatively fast. And then it started moving seriously. So in October 23, portions started to move a foot a week. Now is by far the largest and the fastest moving landslide in the US. If you know of anything larger or faster, speak now. Portuguese band landslide had, in 1956, about 170 residences. 30 remain today. There are those who don't want to move. This Altamira complex now affected 400 residences, and that is how my infrastructure project became a residential project. Let me show you a little bit of geology. So this is geology before Altamira landslide started to move. So you can see here in the legend, there are historically 5 landslides. Abalone Cove landslide here, which has its own abatement district. There is this, beach club. There is, Klondike Canyon, and then there is this Portuguese bend landslide, which is most popular, which made, cover pages in newspapers, and that I will talk most about it. And there are a few other landslides. Now, what is important to see here is that, this was mapped as active historic. This yellow one was dormant old relic. Geologists knew it was moving in the past, but nobody could tell was it 200 years ago or 500 years ago or so on. It wasn't moving much. This Portuguese band was relatively well instrumented or surveyed. So this red triangles are benchmarks. So they were surveyed, and luckily there were a couple outside of this area, which were surveyed, and they showed practically no or zero displacements. Now, this is how residences within the Portuguese band landslide, those 30 that remained, look like. So you can see people kept fixing. They refused to move, and they kept lifting them up and up and up. And those of you who took a field tour last Saturday, you've seen this, what we call a ski jump, which goes up and down. Well, this is this ski jump, just up the hill, which is now not accessible, for various reasons. Some residents are even on skids, so people put the resident on the skid and can move with a landslide. They are fine. They obviously, utilities, quite often interrupted, so you may not have, internet or power, and they're all on septic systems. And what's interesting is that, some of those septic systems were initially accused of causing landsliding. It is now preserved, so, there's no new development. It's a nice hiking trails, unfortunately not accessible, but, hopefully one day it will. Now, the project and all the action started by damage or impacts on infrastructure. And there is some critical infrastructure here. There is this, what we call Palos Verdes Drive South, which is a road which serves, like 12,000 people, emergency services. For most, residents, it's the only way to go to Long Beach to work and come back from work. But also, there is a sewer line, and sewer line is, as you can see here, the ground surface, because you have to fix it, and they keep fixing it sometimes twice a week. There are 2 of them, you put one offline, fix another one, then, put the other one offline and fix the other one. But I don't know how well you can see this here, but these are like 1-foot segments. So each, week they keep adding 1 foot segment just to make this, sewer line, basically service 12,000 people. Needless to say, the drainage is also damaged, so we have water ponding behind, the road, which again, residents many of them thought that that's the cause of landsliding. So, in summary, this is what I found, or we found when we joined this project. 70 years of investigation since 1956. 476 geology and some geotechnical reports. I had a staff engineer to look at all of them, and with one question, find me one which does not end with, we need more data. And he actually did find one. Cause of landsliding, nobody argued that the water is a cause of landsliding, It was just, well, what's the mechanism, But, everybody thought, discussed was, water flow within the landslide. Source of this water, comes from, ponding behind the Palaferis Drive South, cracks, leaky sewage tanks, mitigation measure, pump and dump, and I'll show you in a moment. Even this pump and dump was very restricted because nobody was allowed to do much in the preserve. That's kind of public space, so you cannot access. You don't want to damage, the wildlife and the path. And certainly you cannot touch and cannot do anything at the beach. So we came and look at this, and this is how simplified Geo-Logic, column looks like, a profile. So you have a landslide debris at the top, then you have something which is called Portuguese tuff, which is like, high plasticity clay. It's very good hydraulic barrier. This is what they use in like geosynthetic clay liners, which varies in thickness across, 1 mile or even more. Could be, from 1 inch to several feet, and that can also shear within. And then you have bedrock, what geologists call Monterey Formation. And this mitigation method that we found was, drill a well in landslide debris and then keep pumping, And if it's moves more, add another well. Stops, next season starts moving again, add another well. All across this area I showed you on the map. So then we came and we said, there is enough data, 476 reports. I don't recall when I had this much information in my career. Predominant cause of landslide is likely artesian pressure at the toe. Most likely source of this artesian pressure is this Valley View graben, which I showed you on one of the first slides, and this, like something big graben in the middle of the hill. Mitigation measures release artesian pressure, but it's absolutely paramount that you also do a source control, because you may release it, but the next season it will build up again, and your vertical wells may get sheared off. We also said, we can avoid, disrupting the preserve and bugs and bunnies and whatever they eat, and we can do that by directional drilling, but, we will need access to the beach. Now, in this business, there are, opinions differ, and if over 70 years, people have developed certain, way of thinking and what it is. Some convincing is needed. What I showed you on the previous slide, you can do a technical proposal, but some work with the public and and others is needed. So here's an example, how we dealt with it. So you build a small model like this. So you have a water bottle here, you have a plastic valve here, you have pipe. You put a weighted puck, something weight in another cup. And then you show that to the public or whoever, all the experts involved. So you open the valve, water flows, puck goes up, then you close the valve, puck is still up, then you cut the pipe, and then puck goes down. And you can also use analogies with the, boat at the beach, and then water goes up and boat moves, and show a relatively flat surface. And yes, you can acknowledge other sources of landsliding, like there's no doubt that coastal erosion plays a role in this, but there is really very little what you can do about that. So with that, you can develop a conceptual model, which we did, and this is a conceptual model just for this part of this large landslide complex called Portuguese Bend. So here's the conceptual remedial measures in conceptual form. So within the red line, there is the landslide. So what I would do first, I would cut the source control. If I have a magic wand, I would cut a deep trench, and water cannot come in, cannot feed the artesian pressure at the top, and then I can, drill and release it, and hopefully we are done. But that is not feasible. So the other way to do it is to install a series of horizontal or directionally drilled wells here at the toe, access permitting, and then hopefully intercept as much as you can, and then work at the source, which is above, which is unfortunately in another city, and there are a few agencies involved. So those of you who practice in Southern California, you know how easy or difficult it is to put all of this together. But then in a concept, that's it. And once you control the source, then you can come at the toe, and you can poke few holes by directional drilling. We call them hydroaugers. It's the same technology used in fracking. Just no fracking, but a mistake I made, it was mentioned fracking, that generated 2 weeks of discussion. Up to 1,400 feet long. You can do it here from the beach. That's the best location. I'll show you why. But you can do it also here, what's called initiation point, and the other side Portuguese point, because these are bedrock outcrops. They don't move. Actually, at least we thought until 2004 they don't move. And you can do it from this side, and you can do it from here, and hopefully, mitigate this. I'm not saying, stabilize, I'm saying mitigate. A little bit details. So here's this, geologic column simplified. So you need to poke a hole below Portuguese stuff, because this is where pore water pressure, artesian pressure builds up. Here's the big machine, how it looks like. At the source, you can use the same machine as the source control at the top of the hill of the landslide. Then you can use it for, at the top of the landslide, to relieve artesian pressure. Now, some convincing is needed here, because people, you don't see much of this, in especially Southern California. Saying yes, we did it at the FRB landfill, and we did it in Sunshine Canyon landfill, so it's no good. So you have to do, you need to do some modeling. People like modeling. Whatever computer program spits out, that must be good. So Mr. Withoff, who is here in the audience, developed a square mile finite element model, steady state seepage, artesian pressure at the base. We also developed, I'll show you later, limit equilibrium models of the same area, artesian pressure included, hydroaugers at the top of the landslide included. Did few, follow the proper process, which is develop the model, back analysis, model calibration, model validation. We knew how much it moves, so we could do pretty well, validation, calibration. And then we did forward analysis with and without, drains. I will show you results here only for this, what's called 1 and 1 for two blocks. So basically the part of this landslide, southeast part of the landslide, because proper way to do that is not to experiment on a scale of 1 square mile, to do the pilot program and value engineering and proof of concept and so on, what comes with this type of modeling. So here are sample results. This is a limit equilibrium model here with and without hydroaugers. Without hydroaugers on the left, with hydroaugers on the right. And we could clearly show that we can not stop, but mitigate landslide by relieving pore water pressure at the road. And this was also the biggest concern because this also saves or affects or slows down the landsliding at the critical portions, protects the road, protects the sewer line, and a few other things. Okay, so after all of this, you go into remedial design. So it's a pilot project, and we also needed, we also like to use value engineering because there are issues. I mean, even though there are 476 reports and about 1,500 boreholes, it's geometry of the failure plane is not, it's still a guess. And you really, with this directional drilling, you want to go below the Portuguese stuff, And for that, what you do is you poke few holes and you instrument those holes, and you have a pretty good idea about geometry, and then you can go below that and install directionally drilled, hydroaugers. So what I'm showing here is one of the steps, one of the pieces of information that we had. So this is, in red is basically a basal failure plane as we understood before we started, a pilot program. In blue is, groundwater within colluvium, within landslide debris above the Portuguese bend. I'm not showing here artesian pressure. That was a little bit more difficult to guess, but I'll show you some information later. And I will show you cross sections. And I will show you cross sections here. This is this one AA, which we believed it's much better candidate than BB. But we had to have both. Actually, we had 3 sections because up to the last moment, we did not know if we will get access to the beach and be able to do, what we needed to do from the beach. There was intermediate one, which I'm not showing all here also, which was also restricted access. And one along the Paulus Ferris Drive South is one at the top of BB, and you will see once again on the next slide why the one at the beach is the best. So here's a cross section we call it a beach club, and here you have a Portuguese, tough, relatively well defined, established. It's not that deep or not thick. It's easy to do pilot program, because you need relatively shallow boreholes, and the most importantly, you don't have a failure surface, which I show here in magenta from the neighboring Klondike Canyon landslide, messing up or intersecting. At least that's what our geologists thought. That is not true on the other section, which is high up, so you have a more complex, geometry. And there is, I have it here in question marks, is a potential that those 2 failure planes cross each other. It wasn't known at the time we did this. And if the failure plane of the neighboring landslide crosses through failure plane of the landslide we try to mitigate, then it can impact those hydroaugers. Even though those 2 landslides we had displacements measured, they moved more or less in sync, and at the beach was basically no differential, displacement. There were some above. Now, this is the situation that, we did attempt to, demonstrate, do some numerical modeling, and you can do it relatively easily, like in L-pile analysis, or, you can do finite element, but that's didn't fly. People wanted more. So that is a situation when you actually need to involve rocket science, to keep the project moving. And I will show you in the next slide how this looks like. So this is one design details. We had 35 sheets of design details just for this small area. So you have basically hydroauger within a steel pipe. So carbon steel pipe, 16-inch diameter. We were considering various, dimensions. Some calculations to, come up that felt that 16-inch, found that 16-inch would be fine. And then you have, as you move down beyond what we thought is this interference from the, Klondike Canyon landslide, which I have here in magenta arrows. Then we also had it cased for some time. I think this was, 80 feet, and this was 50 feet, beyond that cased in a smaller hole. And then you have a pipe in between, the PVC, in between, and then another pipe inside. And there is lots of gap. So even if this starts bending, it's, it can accommodate relatively large displacements. It's the same principle if you build a tunnel across the fault. You put a smaller pipe in a bigger pipe, so if it gets bent, buckled, you still, buy some time to relieve adhesion pressure. So, as I mentioned, this was all difficult to explain to those who don't do this for a living, who don't have geotechnical background, who don't have background in numerical modeling, so we did this. Rocket scientist involved. Sort of. And here's his famous quote. "One good test is worth 1,000 expert opinions." We had, I think at one point, 26 experts commenting. So, okay, let's design an experiment. So here's the experiment. Good test, that he calls. Drill 2 pilot holes close to each other. Case one of those holes, case it with a recycled carbon steel, it's not, as large and as thick as we have, for the design, but, something, which, everybody agrees. I think these 7-inch holes. Then, one is cased, one is not cased. Then penetrate well below Portuguese stuff into the bedrock. And you can do that with sonic drilling. You don't need to change the drilling technique when you switch from colluvium into, Portuguese stuff and then into bedrock. So sonic drilling, and, then let's instrument this pretty well, so monitor displacements with shape arrays. So real-time is almost near real-time monitoring, and, monitor pore water pressure below and above the Portuguese stuff. And in the profile with the vibrating biopiezometers, basically what does matter is the differential. We thought we will get pore water pressure above and below, but what does matter is differential. So we did that, and let me show you how it looked like. So this is what I have here on the left. So this is the reading from shape arrays. So you can see here clearly how it progresses in time. 350-foot deep borehole. Nobody expected that it will shear off at 300 feet below surface. Everybody thought that the failure surface is 150 feet down. 476 reports, 65 geologists involved. So this was a surprise. Now, we continue monitoring above as much as we could, and then we continued monitoring, and this looked like, this is Portuguese bend, and then we continued once things get bent and, beyond what was safe. Shape arrays are pretty expensive, so we pulled them out. So we did it by hand, and this is how it looked like. So you have landslide nested within landslide, 150 feet apart, and both of them are moving, at a relatively high rate. Beautiful, isn't it? And there's even movement in perpendicular direction, and discussion on why each of those benchmarks shows a little bit different, rate of movement, and a little bit different, direction is still going on. So this is this Portuguese bend. Okay, and now, well, as you guess, this bottom, of the borehole has something to do with extreme event. And this extreme event started in November 2023 and accelerated April 2024. We first saw it in boreholes. We stopped the program of installation of those directionally drilled hydroaugers because of this. Suddenly, 400 homes affected. 21 homes have been red tagged, 38 homes yellow tagged. Most of the homes, lost at some time, electricity, water, sewer, it was, really a difficult situation, really, sensitive for people, affected. During the field tour, you saw a different location. This is one which is now fixed, so this is how it looked like. It made those who were not affected also nervous, because if the landslide suddenly triples in size, will it grow bigger and bigger, So I have some, I show here in the bottom right-hand corner is a few nice houses, people got nervous. I got nervous because my infrastructure project became a residential project, and most geotechnical companies don't do residential. So, good news is that emergency was declared, both at the local level and the state level. And when emergency is declared in the state of California, then no formal permitting is required. No environmental report is required. What is that? Coastal Commission, so those of you who practice in Southern California, believe it or not, permit within 2 days, temporary permit. Suddenly, no access to drilling or drilling restrictions, and so on and so on. So, our favorite rocket scientists would nowadays say, one good extreme event is worth 5 years of permitting, at least in state of California. Okay, and let me, close this with few slides and few, things what was done, after this extreme event. So, in the meantime, we got more information, more instrumentation available. So what you see here is basically displacement vectors before and after and processed, and you can see that, pretty good idea how much it is moving, and in what direction. It doesn't mean it's not moving. For example, here it means there are no benchmarks, no survey. But we had LiDAR. We attempted in the past to use INSAR data satellite. It didn't work. 3-4 years ago. Now state got involved, and now they did a fantastic job. Nowadays it's even doable from a satellite from above. So there's lots of information about that. And there are significant changes in topography and terrain. And those of you who attended the field tour, you've seen like 500 feet. This is a LiDAR, 500 foot, of new coast pushed out. I think 40, 50 feet. It depends where you measure. Uplift. No doubt. I mean, we've seen at the field tour, like you see shells, just still on top of those, rocks, So, they don't stick for long, for 200 years. So. They were there. So, again, for orientation, so this was the original Portuguese band landslide. This is almost, triple in the size, could be a little bit bigger, nowadays. Failure surface from 150 feet, for this big one, green one is 350 feet. We still do believe that main cause is artesian pressure. I show it here only at the base of Portuguese band landslide and expanded in the Klondike Canyon, is, for a few reasons. But, we know there is, artesian pressure also cause of displacement movement here in the Abalone Cove area in between those two Portuguese points. Let me show you a cross-section, how this looks like in a cross-section. So here's a cross-section, and this is how it looks like. So red is Portuguese band landslide, blue is Altamira Canyon landslide. Actually, it shows pretty well. What I have here on the top, these are shape arrays at various locations that we did as a part of the pilot program. So we have a pretty good idea, not how much it moves, but where is the failure surface. So Pacific Ocean is here. So this is the toe of the landslide. So toe of the Portuguese band landslide is just at the coast. We saw that during the field tour. Now notice how this is all horizontal, relatively horizontal. There's not much driving force here. So that's another confirmation, for artesian pressure, especially this deep one, because the data boreholes, which would all advance below the failure surface, are relatively horizontal. So by this point, you're probably wondering what is BBB on my slide, and it's highlighted in red. Well, this stands for big, beautiful boreholes. And here's one in the cross section. And, the range in depth at the beach, between 300 or 200 something and 340 feet. And this was location and the solution, which, is likely not permanent, was decided by a committee, so everybody got together, everybody involved, including the guy with the, sign, and we concluded that, to help those, 400 residences to mitigate this as much as we can in a short period of time we can. This was very fast. That the best thing to do is to drill BBBs. So, did they work? Well, peak movement was 1 foot a week. After 11 of them were installed, and now there are more, 1 to 3 inches a week. So it did do something. It did definitely confirm that artesian pressure is the main cause of movement. Now, for 50 years, people were pumping water out of boreholes, so we are still pumping 270,000 gallons pumped so far, lots of water, No problem to release it in the Pacific Ocean, even though it's, its location's orange, and some people claim even it may have arsenic in it because it's an emergency. Here are the locations. So this is, for those of you who attended the tour, we've seen this one, which is now the best visible. The others are covered just to protect the beach. And, there's access from the beach club wasn't granted. So access was, from someplace here. Some of you asked me about the grading. So there's lots of grading just to create access so one can not only install but service and maintain those boreholes. Some had to be re-drilled. But that is the situation, and you can see this, from a high-resolution drone photography. So you can see, some boreholes are here because of the access. This is, along here, the beach. Beach club is here. They have their own boreholes, deep boreholes to relieve artesian pressure. They did not believe in artesian pressure for a long time, but now they do. A little bit to zoom in. Now you can see here this, beach extension due to landsliding along the deep failure surface. You can also see beach uplift, now there's a little bit more. And for those of you who haven't seen, not familiar, for example, with shape arrays, they come in a box like this, like a 1.5 log segments that you lower into the borehole and then you pull them out. This is what comes out from the soning borehole. So basically material comes in plastic bags and then geologists come and open it and inspect and log, so information is done. This is how these big, beautiful boreholes look at the ground surface. And here's a video.
Yeah, we're almost there. So right before I go inside.
Shooting up because if we found up to 150 feet of artesian pressure equivalent at the bottom of the boreholes, if the borehole is 300 feet deep, it doesn't shoot out. It's in the borehole, but it's all instrumented and measured. And with that, I do have few conclusions and takeaways and few acknowledgements after that. So I think that nowadays nobody doubts that artesian pressure is predominant cause of landsliding, at least within the city of Rancho Palos Verdes. This disruption of, and coming and telling people that what they have been doing for 50 or 60 years or 70, is not quite, what might not be quite beneficial is sometimes needed. And there is a few things that I learned in this project. Like one of the things is that even though I kind of comment in the 476 reports and more data is needed, that may be true because nobody knew. They didn't know, Geologic Associate didn't know that there is a failure surface 350 feet deep down. And if you find one, in the shallow depth, why would you drill deeper? So people didn't. Now, I think this, one good test is worth 1,000 expert opinion is fine. I think that one extreme event is worth, 5 years of permitting is also holds. I'm not sure how much one good numerical model is worth nowadays, probably many expert opinions. And I don't think the story of this is, done, I may see you in Geo-Extreme 2035. Now, there are a few acknowledgements I want to make, here, to people, many people involved, Alan Withoft, who did this numerical modeling, he was assistant project manager on all 9 projects, I guess, in sequence. Mark Vincent is a geologist who actually figured out this artesian pressure business and valley view graben and basically managed to explain us good enough that we were able to develop models and experiments. Gary Lass is somebody who let me work without a contract, millions, because things were developing so fast that there was no time for change orders for contract negotiations for nothing. Li Xing Shao did the same thing, in Malcolm side, they also had some issues of, catching up. They had a Joseph Hakim on site, in a trailer. I think he was writing change orders weekly. I'd like to take, Elias Sassoon of City of Rancho Palos Verdes, who at the early stages of this project, he understood, something else has to be done. This is a problem, and it will become a big problem. He is the one who listened, who let us do this properly, like a feasibility study, proof of concept, then, some modeling, deal with agencies, funding agencies to get some funding for this, and Sam Hout, who made all of this, actually our life easier because he was contract manager for the city and we didn't have to write ask for approval of, direct costs, upfront. And of course, Tim Stark, who invited me to do this and to do impossible, because it takes about an hour and a half, maybe 2, to properly explain all of this. Thank you.
Oh, that was great, Neven. Thank you. And thanks for helping with the field trip on Saturday with 70 plus people. Okay. So, final presentation in the session is related to the Cache Creek landslide. And I only have one landslide, not 5 or 6 that Neven was talking about. So here's the outline of the presentation. Acknowledgements first. It's a funded project by the USDA. Farshid Vahedafard is the PI. Is Farshid here? No? Okay. Saw him this morning. Some colleagues from UC Irvine, Kaylee Estes, Roxy Silver, and Allison Holman, and from Oregon State, Ben Lashinsky. Here's the outline. So I have a quiz/question for you right here. So don't fall asleep. Right here, I'm going to ask you a question. So what's the Cache Creek landslide? So it's located in Lake County, north of Sacramento, about an hour and a half out of Sacramento. San Francisco is right here, and we're going to end up right about there. So here's an overview of the area, and I think even on this Google Earth image, you can pick out where the landslide is, right there. And there are a couple other important features in the area. One is Indian Valley Dam, right here, earth-filled dam, 64 meters high, so it's a significant dam, completed in 1974, about 50 years old, about 300 meters long, 64 meters high. Main purpose is flood control and water supply. So annually, water is released from the reservoir for irrigation and farming purposes. During the release, hydropower is generated and also recreational purposes, so multi-use. So this is a 1985 Google Earth image. It's not clear, it's kind of out of focus, but there is no scarp in 1985, right there. It's the slide. Okay, so the next Google Earth image is 1993, and you can see the scarp is just starting right there, and this is the eventual slide mass. This is Cache Creek that's running along the toe of the slide. Here's 2021, so you can see quite a bit of scarp has developed from 1993 to 2021, and now we're talking about a slide mass of 12 million cubic meters. Again, not on the scale of what Neven's dealing with, but still fairly large. This slide is what you would refer to as a serpentinite slide. It's a block and matrix material in Northern California that has a very plastic or high plasticity matrix. And you can see it in a lot of road cuts in the area. For example, this one, it's a greenish olive kind of colored material. And let's see, and there it is. If I zoom this up, you'll see some blocks here on the slope face, and that's the block and matrix piece of it. And the clay or fine grain matrix is the greenish material. So this is a deposit that has contributed significant slope stability problems in Northern California. Here's a table that lists some of the larger serpentinite slides. You can see some with lengths of 1,600 meters, so on, 1,500. And here's Cache Creek, 320 length, about 200 meters wide. So it's a big slide, but not the biggest serpentinite slide that's happened. Okay, so now let's look at the impact of the slide. So I go back to this Google Earth image I showed you earlier. There's the slide. Here's Cache Creek. The creek is blocked, and I'll show you just a zoom up of that in just a minute. You'll see that the slide has moved into the creek. It's impacted the creek, narrowed the creek, and so it's a lot of flow going along the toe of the slide, eroding the slope toe. Okay. And one other important piece to understand is Cache Creek empties out here into the open valley, which is called Spring Valley. There's a community here, mainly residential, some commercial, like a very important winery right here near the exit point of the canyon and the creek, and Spring Valley, the community there. So important to keep that in mind for just a minute. So let's look at the water ponding in front of the slide, or upstream of the slide. Here's the slide, here's the creek, and you can see it's wider upstream of the slide, and notice it narrows considerably right along the toe of the slide. And in fact, at this portion, you can see a little white water in the creek. Because it's narrowed so much, the velocity increases, and now we have some white water occurring. So that is contributing to some erosion along the toe at different times, which I'll get to. And here's photos from the slide mass looking at the ponded creek. There you go. And I mentioned that the dam stores water for irrigation, so annually water is released from the reservoir, which all has to pass by the toe of this slide. Okay, so we put some instrumentation in the slide, weather station and some soil moisture gauges to look at the effect of rainfall on soil moisture. The area had experienced a wildfire, so we were curious to see what effects that had on it as well. So here's the hike in. We parked right there, and of course no roads, it's very remote, but there is a fire break right here going up the hill. And actually I shouldn't call it a hill because it's about 1,000-foot elevation change from where we parked to the top of the hill. A rough, highly eroded fire break, so it wasn't really easy hiking. And then we hiked across from the top of the ridge down to the slide and then down into the slide. So to give you an idea of what that looks like about halfway up the hill, there's our vehicle right down there. So you can barely see it. It's a little black dot. And here's carrying in the weather station and all the soil moisture gauges. So it was a pretty rough go getting to the slide. Here's the scarp. So we get to the top and we look over, and it's probably a couple hundred to a few hundred feet, pretty close to straight down, and we said, well, we're not going in there. So we had to walk all the way around the side down to about right here to get into the slide mass. So after doing that, there's the ponded creek from the top. Upstream of it, there's installing the weather station, and it was interesting, there were fresh tension cracks in the slide mass, so it was moving at a slow rate, it looked like. And now, after installing it and hiking back up to the top of the scarp, just to give you scale, that little arrow is pointing to the weather station, right there. You really probably can't see it in this room because it's so far away. And then hiking back out to the top of the ridge and then down. So what are the potential problems here? So the first is a landslide dam. So that there's evidence that the slide has moved and has pinched off the creek, and that backs up the creek, and then if water's released from the reservoir, it has to go over that dam or erode the dam to get through and out through Spring Valley. So in the United States, the last big landslide dam occurred in 1983 near Thistle, Utah, 200 feet high, blocked the Spanish Fork Canyon. Here's the reservoir that built up behind the Thistle slide. And it was so deep, the reservoir, it had to be released with a tunnel under the reservoir that sort of tapped the reservoir, drained it to let it out. There was so much water ponded up, it could not allow it to break the landslide dam and be released downstream. That tunnel and investigation and construction cost about $200 million. So that's what we're concerned about here, that this slide might pinch off the Cache Creek, and then the dam would not be able to release water annually. That would impact irrigation, but more importantly, it rains every year, the reservoir is drawn down through water releases, but then it fills back up during the rainy season. So eventually, that water is going to have to pass, even if it's not released. Okay, so in 1906, a landslide dam did occur on Cache Creek. It occurred 13 days after the 1906 earthquake due to an aftershock. It blocked Cache Creek, and when that landslide dam was breached, it flooded a town downstream of where this slide is, a town called Rumsey, California. That landslide dam was about 30 meters high and impounded about 14 million cubic meters of water. So there is precedence that a landslide dam can occur along Cache Creek. So Indian Valley Dam, 64 meters high, it's got to release the water annually, and if it does, that would back the creek up to the toe of the dam, and now you would have water on the downstream side of the dam, which would not be desirable either. So those are some of the hazards of the landslide dam. We conducted an inverse analysis of the Cache Creek slide, and so we varied the shear strength of the serpentinite and to a factor of safety of 1, of course, and the inverse analysis showed us a friction angle of about 10 to 11 degrees. And given the movement that's happened since 1993, of course, this is a residual strength because of the prior movement. Okay. So we came up with 2 scenarios for landslide dams at this site. If the entire slide mass gets involved and moves along a translational surface similar to the one used in an inverse analysis and shown here in red that goes out to the toe, that landslide dam could have a height of about 80 meters. And so that could back up water as high as 80 meters before it's overtopped, and of course that would release a significant reservoir into Spring Valley, which could have problems for the valley. The other alternative is it could be a shallow slide on the face of the current Cache Creek landslide, and that's indicated by this yellow dashed line here. And that shallow slide would just sort of be a slump off the face of the slide you saw in the Google Earth image, and that would create a landslide dam of only about 30 meters high, which would produce a much smaller water release than the entire slide mass. But those are the 2 landslides dams we considered in our dam breach analysis, which I'll show you in just a minute, to see what level or distance of inundation and impact on Spring Valley would be in just a minute. Okay, so that's the landslide dam. So let me turn to extreme events. So here are the extreme events we're considering for this site. There are 2, 4, 6 of them: wildfires, drought, extreme heat, rainfall, earthquakes, and the flood I was mentioning. So the area has experienced wildfires. Here's a map of the area. And since 2015, let's see, the dam or the slide is right there at the blue area right here. So the 2018 Pawnee wildfire actually burned the slide area. But in 2015, there were 3 fires, 2016, 1, 2017, 1, 2018, 2, and so on. But one of the 2018 fires actually burned the slide mass. And that's why we were curious about installing soil moisture gauges there. So let's look at the drought, heat, and rainfall over time. This is a plot of the Palmer Drought Severity Index, or PDSI. If this index is less than -4, we're in a drought. If it's greater than, or +4 or greater, we're in a wet period of time. And so that's this blue line that's going across here. And if I put 0, that red line is 0. So we're in dry period below this line. Drought, of course, is down here at -4. So there are a couple points to look at. Here's the Pawnee fire. In 2018. So notice the PDSI is -1.2. So that makes sense, a dry period. Then in later, about 2020, about 2020 or 2021, look at the index. It's now as low as -0.56. So a drought period, and again, another fire. And then if we go back to 2015, where we had 3 fires, notice -3.6. So pretty good correlation between the PDSI and wildfires. I'm going to come back to this graph and then correlate it to movement of the slide. So just wanted to introduce it here. And this is data from 1980 to 2023. Okay, earthquakes. I mentioned the 1906 earthquake already and the landslide dam, but since 1968, there have been 31 earthquakes in the area, magnitudes ranging from 1.7 to 4.6, 64 earthquakes with a magnitude greater than 4 within 50-kilometer radius of the slide, 2 earthquakes with a magnitude greater than 5 in 2016. But from 1968 to 84, 36 earthquakes with a magnitude less than 2.9. So a seismically active area which could also facilitate movement of the slide. Okay, now let's talk about floods and this dam breach analysis. So remember, I had 2 heights of landslide dam, a short 30 meters and then a higher one. So there's the dam, here's the landslide. Right here, dam, landslide. Okay, so if the small dam is breached by ponded water, the inundation zone would go to about right there. And if a large landslide dam is created and is breached, it would come down to this area, and Spring Valley starts right about here. So Spring Valley would be inundated by the large landslide dam breaching. So the dam breach analysis, with the small dam, it would have a flood of about 2 to 4 meters deep and have a velocity of about 1 to 2 meters per second. The large dam would have a depth of about 7 to 11 meters and a velocity of about 3 to 4 meters. So those are the extreme events that are possible. So what's happening with the slide currently? So the first, I'll look at topographic displacements, then I'll look at some INSAR results and some surface displacements. Then I'm going to ask you about the perceived hazard and risk. So topographic. So we use LIDAR DEMs and other DEMs, 1953, 2016, and 2021. and cut two cross-sections through the slide, number 1 and number 2. And I'm going to show you the change in the DEMs over this time for each of these cross-sections. So cross-section number 1 is shown here. So it moved about 10 meters between 1953 and 2016. Between 2016 and 2021, not much movement, and that's because you can see there's not much difference between the red and blue line right here. So 1953 is this black line right here. So notice here's the formation of the scarp, right, between 1953 and 2016, and then down here at the toe, some increase in height due to toe bulging and moving into the creek. Obviously, this bulge here is much smaller than the scarp, and that's because there's been erosion of some of that slide mass by the creek over years, and that's why you're not seeing a similar height at the toe as you do in the scarp along cross-section number 1. On cross-section number 2, here's the scarp again, and now you can see the bulge at the toe pretty well here. Even with some toe erosion over the years, still there's a big increase in height along the toe from 1953, which is the black line right there, to 2016 and 2021. Yep, so there's the scarp and there's the toe bulge. So now we can compare the slope or slope geometry between cross-section 1 and 2, and that's shown here. Cross-section number 1 is blue. Let's see. I think I got those labeled wrong. Blue is number 1, 2, and this is number 1. So a little steeper along the blue. This has a little steeper at the toe there, but pretty similar slope geometry across the slide mass. Okay, so let me turn to surface displacements. So we monitored 6 points across the slide mass using INSAR. 1 and 6 are not going to move much. They turn out to be on a rock outcrop. So I'll show you data between 2, 3, 4, and 5 of movement with time. We performed this analysis using C-band imagery. Every 12 days, we were able to get an image. There's some details on our coherence and so on. Here's the plot of movement versus time of those monitoring locations 2, 3, 4, and 5 between 2014 and 2023. So you can see a general trend of movement with time over, let's see, about 9 years. So we tried to correlate that movement to creek flow. So on the bottom of the graph, these gold dots, this is the creek flow, and that's picked up by a USGS gauge just downstream of the slide. So it's really a good estimate of creek flow for Cache Creek right there. Yeah. So if we look here, there's an increase in creek flow here. Notice a little increase in movement there. And maybe similarly here, a little delayed effect, but possibly correlating creek flow to movement of the slide mass. Finally, let me go back to the PDSI graph I showed you earlier, right here, yep. And remember 0 and -4 is drought. So notice there's a wet period right there, fairly high positive value of the PDSI, so a lot of moisture. And then notice this green line is the average trend line for those monitoring locations 2, 3, 4, and 5. So notice here's the wet period, and then shortly after, there is a delay, we start picking up a significant increase in movement. And it's interesting because notice after the wet period right here, there's actually a dry period, but the slide still moves. And I think Neven was kind of hitting on that with his presentation, that you have a source area, it takes time for that source to make it down into the failure surface and out to the toe, and then you see movement. And I think we're seeing that with the Cache Creek slide. The other thing to notice on this diagram are these little vectors. these little vectors are vectors of velocity. So notice the wet period, and now notice the velocities are picking up as well, even though there's a little drought period in between. So using this data, we came up with the estimate that if the rainfall exceeds about 1,700 millimeters, which is about 32 or 3 inches of rainfall during the rainy period, you have a potential for slide movement. And so that's sort of a guide for when people should start thinking about the slide moving more. Okay, and that is 1,700, that line, horizontal line going across. Okay, so that brings me to the question or quiz. So I tried to present that in an objective manner, just kind of giving you the facts and only the facts, right? So, and this is a geo-engineering or geo-professional conference. So how many people would be concerned about the Cache Creek landslide, just out of curiosity? Few people. Okay, all right, good. And I realize this is a geo event. So as part of this project, we had a survey of residents, and it was a wide-ranging survey of residents, and we asked a number of questions, one of which was, what hazards were they most concerned about? Okay? Any guess? You think it's landslides? Okay, so here's the summary. 813 people surveyed, and notice the hazards at the bottom: drought, extreme heat, wildfires, landslides, excessive rainfall, flooding, snowstorms. So I think I heard somebody say wildfires. Absolutely. That's an annual event, and you could see just in recent years, almost every year there's a major wildfire, right? Sometimes many in a single year. The other extreme event that they were really concerned about is extreme heat. In fact, that just tops wildfires just by a little bit. Right? So what did they, how many people were concerned about landslides? Right there, it thought that was a big concern, and the red bar is a lot of concern right there. 2 people. 2 people in the whole survey. So we think that it's a pretty good hazard that the slide is moving. It depends on how much it moves each year, but it can block the creek. The dam has to release water every year, otherwise it'll overfill, and it's an earth dam, so it cannot be overtopped, so it has to be released, right? And if a landslide dam is created, eventually it'll breach and flood at least part of Spring Valley downstream. So we think it's a pretty good hazard, and this shows that we obviously aren't conveying that hazard very well with only 2 people being concerned about it. So something to think about for our profession. How do we communicate these hazards better and more efficiently to the community? Okay, so in summary, multi-hazard project and situation here. We've got a landslide dam, wildfires, rainfall, earthquakes, flood. Using digital elevation models and INSAR, we're able to sort of get an idea of how much it has moved and how much it is moving. And that shows about 10 to 15 meters of movement since 1953. If the rainfall exceeds this 1,700 millimeter threshold, we think the movements will increase, and so that's kind of a good magnitude of rainfall for the emergency responders to know about. And finally, the risks not being recognized. So with that, I hope we got a couple minutes for questions.
We're a little bit over time. We could use the break as a form of questions.
Okay. All right, so where's the break? Right out front?
Yeah.
Okay, so if you have questions, Andy and Neven will stick around after the session. I guess refreshments are straight out the door, and then the technical sessions start. What time's the technical session start?
When we say they start.
When?
That's the last thing, so don't worry about it.
Okay. when Brad says they start.
Are we doing Q&A?
If that's the case, we can have about 5 to 10 minutes of Q&A here while everyone's here.
So I don't know if our speakers want to go back up front, because
Okay, Neven and Andy, come on up. Anybody have questions for Neven, Andy, or myself on landslides?
I'm going to start because I'm holding the mic.
Okay, go
We
ahead.
got one in the live stream in the chat. This is about the Washington Park slide.
Okay, Andy.
Did you instrument any of the piles at the base of the pool?
Instrumenting the piles that were supporting the reservoir, no, those were not shear piles, and so they are not serving any purpose in restraining the slide there. We have certainly instrumented shear piles before, but these ones were strictly vertical floating, so we just had kind of the normal quality control instrumentation for the drilled shaft quality there.
Okay, other questions? Oh, yeah, yep.
Just an excellent group of presentations. Congratulations on that, and thank you.
Thank you.
My question's for Neven. Do you guys know what the material is along the deeper, roughly 300-foot deep landslide plain?
Yes, we do. It's a Monterey formation. This is a transitional block slide. You have blocks sliding on top of the block at depth, and material is Monterey formation broken into pieces.
So it's not the really clay material that we're used to further up?
Actually, what geologists tell me is those blocks move, they grind the material, Monterey formation. If you do that over extensive period of time, it becomes pulverized, you squeeze it, becomes pretty good hydraulic boundary, which then can retain artesian pressure. Diatomaceous, yes.
Other questions?
Excellent presentation. Question about the Washington landslide. If you were, we are to design, nowadays, there's a bunch of places we're going to be designing those reservoirs, from now on. How would you, if it's not moving, right? Now we have the tools, we have the resources, drilling and all that. How would you identify that might be happening? Because it's so sensitive. They're excavating some, 60,000, I think, cubic yards at the toe. And you have like this huge, massive landslide moving that you don't know it's going to move, right? How can you identify and, communicate that to the client that, I cannot just go this much deep. I need to go way deeper because it's going to be a problem.
Yeah, so I think, is your question a hypothetical situation where we are constructing within what we think is an ancient landslide, but there's no surface manifestations of that?
Correct, yeah. If it's today, right, like back in the 1900s.
It is a challenge. There's any place where you're constructing, there's a lot of unrecognized hazards, right? And, a good geologic characterization of the site would probably flag. I think that there would have been indications at the time, if they had had the geologic knowledge we have today, that this had moved previously in the past. But it is a challenge because you don't know whether your factor safety is 1.01 or it's 1.1 or what it might be. And so, the way that we have approached that before is, there's lots of upfront risk disclosure, right? But then you're also saying, hey, I'm going to characterize this the best I can. I'm going to give you my best estimate of where we're at here. But we're going to have several different thresholds of different contingency options for this. And depending on the magnitude of the importance of the infrastructure at the toe, you may be doing things preventatively that, spending money in order to mitigate your risks because you don't really know where that factor of safety is at.
I have also a question for Andy.
Yeah.
That those tunnels that are over 100 years old, did they have drains that fan out? And over the last 100+ years, can you tell us how they were maintained so that they wouldn't clog?
Yeah, that's a great question. There were no fans, let's say, but I didn't have time to show a map of those tunnels. They do finger everywhere across the slide, so it's not just a linear tunnel up and down the slide. It branches out into many different locations. And what they did is in the 1920s, they went in and backfilled them with gravel so that as that timber cribbing decayed, it wouldn't collapse and cause sinkholes. But that's the extent of the mitigation that's been done for those. You know, we don't have an exact location for the majority of those tunnels. We have their old maps, but they haven't all been located. So really the best indication we have right now is measurement of outflow at a couple of the known locations, and just kind of keeping an eye on the outflows to see whether those are changing significantly over time.
So question to all three presenters. For all of your case, currently under the static condition, the factor safety equals what? So what's your opinions when the earthquake comes? 10% in 50 years, 2% in 50 years, how much the slope go?
Well, there are a few NDAs I had to sign, and I'm still on the contract with the city, so I will disappoint you.
Andy, you go next.
We did look at that for the Washington Park landslide, and we did a number of different numerical modeling on a Cascadia subduction zone because that was part of the seismic. The seismic was a driver for this project. I think Chris Meehan and some others have done some good work to show that your factor safety is one under static conditions, but a lot of times these clay materials that form the base of your slide plane are going to have rate-dependent effects that are going to keep the displacements lower than what you would think if you just ran on, say, a Newmark analysis with a factor of safety of 1 as your starting point. And so we were estimating somewhere around a foot of movement during a design Cascadia event for that case.
The 1906 earthquake aftershock did induce a landslide dam, so we think the potential is there. We did not do a deformation analysis yet.
I have a question for Tim. Actually, I have two. Maybe a two-parter, maybe just two questions. One's on the risk to the community about the landslides. So I just wanted to get clarification on a couple of things. One is, it wasn't just landslides in general. You had clearly laid out this scenario.
Great question. In the survey, we did not lay out the scenario. It was a general question of landslides in general.
Because they're out in the flat, so.
Right.
All right, so that clarifies it.
Right.
But I'll just follow up then, because this is really the basis for the question, because had they known, their livelihood of farming is actually disrupted at minimum. At maximum, they're washed away. And the other part is on the extreme events. You kind of laid it out, but you didn't put heavy rainfall as an extreme event like an atmospheric river, because they can get a lot of water up there in a very short period of time. So I'm kind of curious on your thinking about why heavy rainfall wasn't listed as an extreme event.
Great question, Greg. So the reason we didn't list it is at the end of the summer, they try to have the reservoir down very low, and you'll see big bathtub ring right around it because the main purpose is flood control. So they basically try to empty it so they catch the 100-year. So there have been 2 100-year events there at Indian Valley Dam, and they were both contained. So that's why I didn't harp on it too hard.
Okay, but you could, if they actually had it would fill up. You laid it out, but you just didn't.
Yeah, because I didn't want to say, well, if you get the 100-year, you're going to have to pass X amount and so on. Because the goal is at the end of the summer to basically have full flood control capacity. That's the goal. Okay. Yeah. But no, good, excellent point. Okay.
So this is going to be our second to last question, then we got one from the live stream, and then we're done.
Okay.
Great presentations all. This question is for Andy. I want to know when you mentioned about APS geofoam. So we know that like geofoams, can be considered as compressible materials, but also when it, to a certain extent, right? So when it gets compressed, it becomes stiff, and then it can potentially apply the load against it to the structure, right, adjacent structure. So when you guys evaluate the, materials that you feel like is going to be a good choice for that condition to fill the gap and to minimize the impact of the landslide movement, and then also the MSC wall movement, is that, did you guys decide that APS probably is the best choice because of the long-term performance, or is it, and also I wanted to ask if to make sure that it's going to perform long-term well, did you guys kind of like cover it to protect it against moisture or any, exposure to water or anything like that?
Yeah, that's a really interesting topic that I could probably do a whole presentation on, the design of that. There's, to the first part of your question, EPS was the material that we determined would give us the best stress strain behavior for this. So you have your initial linear response, then you have a very plastic response before you get to the strain hardening. And so we designed it for a strain that would keep us in that plastic range. And so I could talk with you about that sometime. One of the factors that plays into that is because the landslide movement is seasonal, you actually have a lot of creep behavior in that. So you get sort of cyclic up and down stress alterations there. But, yeah, that was a deep dive in and of itself. We did cover it. It has a membrane liner. There's really not a lot of risk of exposure to petroleum products, but it was isolated. And then there's the opportunity, if the city needs to extend the life of it, to replace that at some point in the future. Yeah, I think that the most sudden movement would be during a Cascadia subduction event, something where you could have, a foot of movement over, a matter of, seconds to minutes. There's a lot of dynamic things happening during an event like that, and that was something that we kind of discussed with the structural engineer and came up with some ways of modeling to make sure that the reservoir could handle that.
Okay, so we'll close with this question. Should practitioners routinely survey precisely the tops of SAAs or slope indicators to confirm that the instruments are seeing all the movement?
How can we say no to that?
So I think we're good then.
Yeah.
So Tim's ready to get off the stage. So
Okay.
we do
Well,
have.
I'm getting the hook up here.
We have something else to do. So you say what you got to say to get off the stage, and then I'll take back over again
Okay.
for the last couple minutes.
I want to thank Andy Kost of Conforth Consultants and Neven Matasovic of Geo-Logic Associates for 2 excellent presentations, and all of you for attending our session on mega landslides. So thank you very much, guys. Way to go.
Before we go to the break, this is the last time we're all going to be together in this room, so I want to have Daniel and Neven come up here.
Absolutely.
They might have a few closing remarks for you. Do you guys want to do that first? No closing remarks? Good. Then you guys get these. Got a little something for you. So before we do the photos, when did we have the first meeting to start planning this event? 3 years ago. I hope it looks like it, but it takes a really long time for us to plan stuff like this. 3 years, and we met, every other Friday, I feel like, for that whole time. Some weeks you get together and there's not a whole lot to do, and then some weeks you're like, an hour's not really going to cut it, and then there's email traffic throughout the whole week, and it's a lot of work. So to be the chair of any conference is a lot of work, so we really appreciate it. And I always feel bad giving people the plaques because I'm like, you spent 3 years of your life on this, and here's Yeah, a piece of laminate with like an acrylic thing on it. But I mean, dang, it looks good, right? So let's big hand for Daniel and Neven and all the work they put in. And after we do a couple photos, could the rest of the program committee come up and we'll take some pictures too? And if you're thinking to yourself, was I on the program committee? You were on the program committee. So come on up after we get a couple. And we will start the last block of sessions at 10:30. So everybody be in your session rooms at 10:30. And thank you so much for coming out to Long Beach this week and spending it with us. We really appreciate it.